So, good afternoon, everyone. You can hear me? Okay. For those of you who don't know me, my name is Matt Ricci. I'm a postdoc at the Data Science Initiative here at Brown, and I'm very pleased to welcome you to today's second Data Wednesday presentation. We had a busy day today. We have an excellent lineup of speakers this semester, including next week's presenter, Charalampos Tsourakaki's from Boston University, who will speak about dense subgraph search. Please note that Professor Tsourakaki's talk will be held at 2 p.m. instead of the usual 4 p.m. Today, we are very lucky to have with us Professor Robert Grice. Professor Grice is an applied topologist who holds the Andrea Mitchell University Professorship in the Departments of Mathematics and Electrical and Systems Engineering at the University of Pennsylvania. Professor Grice studies applications of topology to dynamical systems, data science, engineering systems, and more. Today, he will present research on social network dynamics in a talk entitled Opinion Dynamics on Sheaves. Now, will you please join me in welcoming Robert Grice?
Thank you very much. I really appreciate the invitation. I really appreciate those of you who are here being here. So I'm going to give a talk that is, I don't know, reconfigurable. This is a diverse audience, and I want to make sure that the sometimes a little bit complicated mathematics that I'm going to bring to bear on a hopefully interesting problem is understandable to everyone. So please feel free to ask questions in the middle of the talk as well as at the end. So if you don't mind, I'm going to take just a moment here and do a share screen. And instead of death by PowerPoint, even though I love PowerPoint, we're going to be a little bit more freestyle. So this is joint work with Jacob Hansen, who is a PhD student of mine. He is now a postdoc at Ohio State University. And some of the work that I'm going to talk about today appears in his PhD thesis, but a lot of it is follow-up work that we have done since. Okay, so this all goes back to a classical problem of looking at opinions on social networks. So if I think about how information, opinion, ideas flow over a social network, there's obviously a lot of interesting phenomena that can happen. This is very clear from reading my Twitter feed. I don't really do Facebook anymore, but definitely on pretty much every social network, there's always all kinds of interesting dynamics going on. Now, people have been modeling dynamics over social networks, opinion dynamics for quite a long time. This is an absolutely huge literature that there's no way I can do justice to. So what I'm going to do is I'm going to start off with a really, really simple story and then talk about what begins as a simple generalization and then gets a little less simple. So consider the following sort of cartoon scenario. This goes back to work of Taylor that is building, and this was what, I think it was 60s, 70s, a long time ago, right? Anyone who's born then is like really old. And this follows on earlier work from 50s and 60s in even a more primitive context. But here's Taylor's setup. Let's say that we have a network, a social network that is an undirected graph G, and the vertices are, of course, the people in the social network, and the edges are going to be relationship, friendship. This is more like Twitter than Facebook in that it's not directional. Pardon me, I got that backwards. It's more like Facebook than Twitter in that it's not directional, right? On Facebook, friend is an if and only if thing. for a typical Facebook account, whereas Twitter can be one way. I can follow you, but you don't necessarily follow me. We're going to work in the undirected case. Now, in this simple cartoon context, what we have is some topic, and everybody in that social network has an opinion on that topic. Now, opinions aren't quite the same things as preferences, but there's often a lot of confusion in the literature on this. So if you want to think of this as a preference, you may. And this is modeled as a real valued variable, by which I mean I have a copy of the reals, and you can have a very, very strong positive opinion, or you can have a weaker positive opinion, or you can have a negative, maybe a very, very negative opinion, or you could be close to zero, which is meh. I don't care. Let's make this real. Okay, so today, for today's talk, I wore the pink shirt. I don't know. What do you think? Is that a bold move? Some of you, thumbs up. Some of you maybe. I don't know. It goes well with the tie. What do you think about the tie? I don't know. Pick one. Pick the shirt. Pick the tie. Maybe you like the fact that I'm wearing a suit. Sign of respect. Maybe you're like, can I trust a mathematician who wears a suit? I don't know. Pick a topic, and then everybody has an opinion, positive or negative, or whatever. I don't really care so much. Now, what happens is we have social dynamics. People talk, people share their opinions. There is rational discourse, there's consideration and mutual understanding. And over time, uh, after talking to my friends, my opinion might drift, it might change. What Taylor did was he set up some dynamics and used, in particular, the graph Laplacian. The graph Laplacian is a classic construct from graph theory. This can be thought of in terms of the adjacency matrix for the graph and a diagonal matrix that encodes the degrees of the vertices, or you can write it in terms of the boundary matrix. Either way, you've got that graph Laplacian, and it really is like a Laplacian in that one can set up a heat equation that is spatially discretized according to the graph. So what we're going to do is we're going to have a vector of opinions. So this is going to have one opinion for every vertex of the graph. So these are the vertices right here. Okay, and then the heat equation says, well, your rate of change or your flow is going to be related to the Laplacian of x by some negative constant. We could use alpha for the strength of the diffusion. This is really just nice, simple heat equation. And what this means is that every person talks to their neighbors, and they look at the difference between the average opinion of their neighbors and where they are, and they just change a little bit to move towards the expressed average opinion. And then the theorem that results very, very easily is that no matter what your initial condition is, this is going to converge to a constant, just like a plain vanilla heat equation. You just let it go and then boom, constant temperature. But what it means in this context, of course, is a consensus. Everyone comes eventually to the same opinion. And then the lesson from this is that, well, if we pick our favorite topic, whether it's my shirt or my tie or our feelings about the president, and we just talk over social networks, then eventually everything will just diffuse to consensus. And here we live in perfect harmony. That's not exactly the way things work. This is a cartoon model, after all. And in fact, the more extensive the social networks, the more polarization we seem to be experiencing. So this result prompts one of the driving questions in the area of opinion dynamics, that is, how do we account for polarization? And this is the beginning of a huge, really, really rich literature where you've got all kinds of models that are meant to explain the origin of polarization, to explain how you can have waves of opinions spreading over a network, to explain what happens in the context of systems where you have multiple opinions, what happens in systems where some people are more stubborn, or where some people maybe don't quite tell the truth about what they think, etc. Tons of different models, tons of different interesting analysis. What I want to talk about in today's talk is a new model that is very, very similar to this simple cartoon model, but which allows for a great richness in modeling, in expressing different types of behaviors over social networks. And my secret motivation for this is to make use of some really interesting tools from topology. I'm going to take a few minutes to talk about those tools somewhat in the abstract, and then I'll put it to good use. The tools that I'm going to discuss come from something called Sheaf Theory. Now, this is the part of the talk where I don't know if the mathematicians are going to be happy or mad, because, of course, I'm not really going to tell you sheaf theory. If you want to know real sheaf theory, you pick up a book on sheaf theory and see how long you can last, right? I can go about 15 minutes of reading that before I cast it to earth. Your mileage may vary. What I'm going to talk about is a simple version of sheaf theory called cellular sheaf theory. If you've never seen any sheaf theory before, that's okay. You can get the basics of this down, no problem, really fast. Cellular sheaves were invented by Shepard, a student of Bob McPherson, in an unpublished PhD thesis sometime in the 80s. My PhD student, Justin Curry, independently rediscovered this stuff in, 2013. And it appears in his unpublished PhD thesis. And there's some very, very nice, simple, but powerful tools contained in this. What is a cellular sheaf? Well, we have to talk about a sheaf over a space. And a cellular sheaf uses a cell complex. Now, if this were a talk to just a straight up math audience, we'd do things over a cell complex in arbitrary dimensions, and there'd be a lot of nice richness in there. To the mathematicians in the audience, I'm sorry, I'm gonna disappoint you here, because for the sake of concreteness and simplicity, I'm just gonna look at a network sheaf. I'm just gonna take a graph or a network, vertices, edges, a one-dimensional cell complex, if you will. So what does that entail? Well, a sheaf I like to think of as an algebraic data structure. This is not the usual interpretation of what a sheaf is, but I think it's a good interpretation. What we need to do is talk about what type of algebraic data we're going to work with. I'm going to work in the category, like literally, of vector spaces and linear transformations. Asterisk, fine print, all of the vector spaces appearing in this is going to be finite dimensional and based, meaning with an explicit basis in a product, whatever you like. Okay. What a sheaf over such a graph, what a network sheaf, taking values in the category of vector spaces is simply a functor from that graph with the edge relation, something like a poset relation, to this category. Timeout. What does that mean? Oh, what that means is every vertex in the graph gets assigned a vector space. And this is, for historical reasons, called a stalk. You think of it as something that sort of grows out of the vertex vertically, but that's not all. To every edge in this network, we associate a vector space, its stalk. These are not the same. These are not homogeneous. You can have different dimensions at different vertices and different edges. It can be totally inhomogeneous. This is not like a vector bundle. A vector bundle would be an example. A discrete vector bundle would be an example, but this is not really like a vector bundle. Now, to every vertex edge pair, that is, here's a vertex and it lies on the boundary of this edge, or this edge connects to it, then we're going to assign a linear transformation that goes from the data over the vertex to the data over the edge. So in maybe more concrete terms or more visual terms, if I have an edge in my network, then I have a vector space over this vertex, and I got a vector space over that vertex, and I got a vector space over this edge. And then in the same way that the graph is got all these pieces glued together with edges, well, all of these vector spaces, all of this data is conglomerated, is glued together with these linear transformations. And what's really cool is that you can program a sheaf to get it to do what you want. Now, a full explanation of what I mean by that would take a little bit more time than what I have. I'm going to give you a concrete example in the context of opinion dynamics. Before I got to do that, I got to say a little bit about the why. What is going on here? Why do mathematicians care about this? Oh, sheaves are really fantastic for a couple of reasons. They allow you to really formalize the local to global transition. Lots of problems of a local to global variety wind up being converted into problems about sheaves. And the algebraic tool that helps you solve those problems is something called the cohomology of the sheaf. Now, again, sheaf cohomology is a subject that, it gets a little spicy. But in this really, really simple context, it's so simple. It's so simple. Here is the idea of sheaf cohomology in 2 minutes. Here we go. What we're going to do is take all of this data that is in the sheaf, all the data over the vertices, all the data over the edges, and we're going to sort of arrange it in a way that one might describe as a little bit complex. I'm going to take all of the stalks over all the vertices and just add them all up, just bundle them together into a big vector space. I'm going to do the same thing with all of the data, all of the stalks over all of the edges in my graph. Now, what did I have in this picture? Oh, I had all of these linear transformations that went from vertex data to edge data. And what I want to do is bundle all of those up together as well, but with a little bit of cancellation. This is done through what is called a coboundary operator that is really quite concrete and simple. There's a little bit of fine print, just like when you're doing things like a graph Laplacian and you need to choose an orientation for each edge. We have to do the same thing here. And what this does to what is called a zero cochain, a zero-dimensional cochain, that is a choice of data over each vertex, to turn this into data over a particular edge E, what I do is I take the data at a vertex V, and let's say that this edge E connects from a vertex U to a vertex V. I'm going to take the data over V, that vertex V, and I'm going to map it forward by this linear transformation. And then I'm going to do the same thing with the vertex U, and then I'm going to take the difference between these. And the orientation is giving me sort of which way that minus sign goes. So this is a difference in the data over the vertices as expressed along an edge. Aha. And the definition that is so useful is the zero-dimensional cohomology of my graph taking values in this sheaf is really just the kernel of this linear transformation. This makes absolutely no sense the first time you see it, but it is so central to so much in mathematics. These are called the global sections of the sheaf. And what this means from a data point of view is that if I look at my graph and I've got all kinds of vertices and I've got all kinds of edges, and what I do is I'm going to have a choice of data over each vertex, and I want to know how compatible are these choices of data. And I'm going to measure that compatibility by what these project to, what these map to over the edges. And if they perfectly match up, if the difference between them is 0, then I'm in the kernel of this map. Okay, excellent. Now, so what? Well, this is really just the beginning of what one does in cellular sheaf theory in the very, very, very restricted context of vector spaces and networks. Let me talk about a simple example of such a simple sheaf that really can do quite a bit. This is going to be called a discourse sheaf. So what we're going to do is the same thing that we did before. We have a graph, undirected. It's got vertices. It's got edges. The vertices are people. The edges are connections between the people. Now, instead of everybody having an opinion about my pink shirt, you have opinions about whatever you have opinions about. And I have opinions about whatever I have opinions about. To each vertex V, we're going to associate an opinion space. This is going to be modeled somewhat unrealistically as a finite dimensional vector space where there's an explicit basis topics, things on which you have an opinion. And that opinion, it can be positive, it can be negative, it can be 0. So this is really going to be n-dimensional real vector space for some value of n. Now, that's V. What about the vertex U? Well, that goes to a different opinion space. These are not the same. This is the kind of thing that a sheaf was built to do. Now, when two people get together, what do? Do they share their opinions? No. When I'm talking to you about something, I'm not giving a full core dump of everything that I have strong opinions on. No, not at all. Rather, when we are discussing something, there's some topic or topics about which we are trying to express an opinion, come to a consensus. So, with respect to that edge between us, what we're going to do is associate a discourse space. And this too will be based, it will have a basis, whatever the topics of discussion between you and me are. This might have nothing in common with my basis opinions, with your basis opinions, but that's okay because we're not simply just doing a flat share of what we think about things. Rather, what we're doing is we're formulating expressions of opinions. So that's me, that's you. But what we're here to talk about today is this stuff. These maps, these linear transformations, are expressions of opinions, or if you like, formulations of opinions. Now, this is, again, a model. It's a cartoon model. These are linear transformations. That means if I increase the intensity of my opinions, I'm going to increase the intensity of my expressed opinions. So a personal change is going to come out in a linear fashion. If all of a sudden I stop caring about everything, then when we talk, I'm just not going to care. Just not going to care. But here's the thing. This is very expressive as a model for how discussions can go. Why? Because I might be talking to lots of different people about lots of different topics. And, oh, I don't know. Let's look at a really simple example where all of the stocks, so all of these vector spaces are just one dimensional. And let's say that all of these linear transformations from vertex stocks to edge stocks are just a 1-by-1 matrix that is plus or minus 1. What does this mean? This means I'm either, if you like, telling you the truth about what I think about this common topic that we're discussing, or I'm lying. And again, this is a very, very restricted case where we're just picking one topic, my shirt, and we're all discussing our opinions about it. But in that very, very restricted case, then, you know, I can be telling the truth to a whole bunch of people, and then to this person, and this person too. I'm just not gonna. I'm gonna say the opposite. I'm gonna fake it. You could imagine contexts in which that sort of selective obfuscation or even just selective dampening of opinion is an appropriate model for what is happening in a sensitive discourse. Okay. Well, again, so what? So what are we going to do with this? Well, as just a setup for being able to model discussions where you can have selective changes in expression, where you can have private opinions that are not shared. This is really very, very general. But until you have some, I don't know, meaty tools for actually doing things, proving theorems, it's really just a model, just a language. And speaking of language, I haven't used any of that cool Sheaf stuff yet. So let's get to some tools and some theorems. And here is the big tool that is really going to be useful. This is a Laplacian. A graph Laplacian? No. A so-called Hodge Laplacian. This is common in a couple of different areas of mathematics. Let me explain exactly what I mean by this in the context of these discourse sheaves. You will see that this generalizes the graph Laplacian, but we also just get it for free from the algebraic topology associated to this cochain complex. So if you recall, I have all of these zero cochains where I bundled up all of the data over the vertices. And then I have these one cochains, which is bundling up all of the data over the edges. And I have this linear transformation, this co-boundary operator, which is really just a big old matrix, kind of like the boundary matrix for a graph, but it's got all this data in block form associated to it. Well, in the same way that the graph Laplacian can be expressed as the boundary matrix times the boundary matrix transpose, the Hodge Laplacian in this very, very simple restricted setting is going to be no more and no less than the co-boundary operator composed with its transpose. Why does this transpose exist? This exists because everything in sight is based. You can get this to work in more general contexts, but you need some sort of notion of inner product or some way to get an adjoint to the co-boundary operator. But yeah, that works. And what that does is it takes vertex data, pushes it out to data over the edges, mixes it up, and then pulls it back to the vertices so that we get an operator on zero-dimensional cochains.
Can I ask a clarifying question?
Please do.
So it's just terminological, really. So you keep referring to, for example, the cochains as like data.
Mm-hmm.
And I'm familiar with the usual definition of a cochain as a function, so like a function on the vertices. And so when you're referring to that vector space, is there some sense that we should be thinking of the vector space attached to the vertex as functions on the vertex? Like, should we be thinking of it as just the function that produces objects in the vector space for values of the vertex or something?
Yeah, I don't think of it as a function at all, like in the classical cohomology case. I really like to think in a more sheafy way that you have this stalk growing out of the different cells, and you're choosing an element of that stalk.
Okay, and in part, I'm sort of wondering, part of the reason for the question is just that I'm wondering why all of this is being done in cohomology rather than homologies.
Right. So there is a dual theory that is called a co-sheaf that is sometimes, but not always, more appropriate than working with a sheaf. In this context, which is just so dumbed down and simple, yeah, if you feel like doing homology instead of cohomology, yeah, you could reverse everything. But it really, for purposes of working with a Laplacian, you really want to work with vertex data because these are the opinion distributions over people, as opposed to expressed opinion distributions. Those are the one cochains.
Yeah, that makes sense to me. Thank you.
Cool. Okay, let me go back to the screen. Pardon the delay. I got to learn the keyboard shortcuts for doing that, like zing, zing, zing. Okay, now here is a, I don't know. I can't even call it a theorem. because this is such a restricted case, but it is it is a very dim emanation and shadow of the Hodge theorem that the kernel of this sheaf Laplacian is the zero-dimensional cohomology of the sheaf. It is the global sections. This kernel consists of the harmonic cochains. By tradition, that's what we call things that are in the kernel of the Laplacian. But why is that a good name? Well, let's think. Let's interpret. What is an element in the zero cochains for a discourse sheaf? And if you've struggled with some of the jargon, then this is the point at which to pay attention. What is this? This is really an opinion distribution, meaning that every person has some private opinions. You stack all of them into just one big state. That is what a zero cochain means. What is a one cochain? This is an expressed opinion distribution. This is an opinion distribution over all of the conversations that are being had in the social network. What does this co-boundary represent? What this represents is a difference in expressed opinions. That's a very nice interpretation. And what does it mean to be harmonic? To be in this zero-dimensional cohomology? That is, it is literally a harmonic opinion distribution. Everybody is in expressed harmony. Now, everyone still has their private opinions, but in terms of what's being expressed, if I look at what a vertex U and a vertex V says over an edge, they agree. They agree. Even though in private, they've still got their own opinions. Okay. Now, there's more that could be said here, and much more that one can do when one has higher dimensional base spaces, higher dimensional cohomology, but let's just skip ahead to the good stuff, which is a theorem. And this is going to be the sort of Hodge update of this old result of Taylor, namely that given a discourse sheaf over a social network, over a network, and given any initial condition, that is an initial opinion distribution, then if I look at the heat equation, where I use this Hodge Laplacian to diffuse opinions by means of expression maps, then the solution converges to the orthogonal projection of that initial opinion distribution to the global sections, to the harmonic opinion distributions. You flow to the nearest harmonic distribution. Now, this is not a hard result. This is a very easy result. Why? Because this John right here is a linear operator, and you know what the eigenvalues of the graph Laplacian do, right? Well, same thing here. if you want the details of the spectral theory for these sheaves, then there's another paper on that by Jacob Hansen and myself. That's another 50 pages to deal with. Not going to get into that, but the spectrum is really nice, right? You got 0 eigenvalues, and the number of 0 eigenvalues corresponds to the dimension of this harmonic subspace. And then all the other eigenvalues are positive. So we've got this nice symmetric semi-definite operator, and that means, boom, you're going to converge. Okay. That's kind of cool that in such an expressive model where, if you were doing this from scratch, you'd be tempted to just sort of add this piece to a model and add this piece where you can have people lying, and add this piece where we have, nope. Very, very simple model, very, very simple differential equation, very, very simple proof. This is nice. Okay, but, again, what else you got for me? Well, let's see if we can reproduce some of the other phenomena that have appeared in the literature. So one thing that is fun to model is what happens if you have stubborn agents. Oh, well, I wonder if this language is going to be useful. Let's say that we have some subset of the vertex set of the graph, and these are stubborn. These they're not influenced by their neighbors. They just spew out whatever their expressed opinions are. Well, if I were to think about this physically in terms of like a heat equation, this is kind of like some sort of boundary condition. And if I'm looking for a solution to the heat equation, I'm really going to be interested in questions of harmonic extension. That is exactly the right language to invoke here. Here's a fact that you can find in that referenced paper on spectral sheaf theory. I'm not going to be able to define all these terms. Sorry about that, but that's the way it goes. So if the relative zero-dimensional cohomology valued in the sheaf vanishes, then the harmonic extension from you being equal to whatever you want exists and is unique. A harmonic extension will always exist, but it may not be unique. So what this means is that if I look at the restricted heat equation, where I have nice diffusion if I'm off of U and I just zero out everybody in U, then this too converges to the nearest harmonic extension of whatever the initial condition was on those stubborn vertices. And that too is a very, very simple result that sort of validates the use of this language of sheaves and sheaf Laplacian, because it allows you to reason in terms of harmonic extensions and these sorts of things. Well, once you've got that, then you might ask other questions. Instead of interpreting these nodes as being stubborn, what if we interpreted these nodes more maliciously as being something that's controlled? And I use that word very intentionally. What if we control the inputs and the opinions that are being shoved out into the network? Can you drive opinions? Literally, can you do a little bit of control theory and control opinions. Now, there's a bit of a long story here, but a little bit of classic control theory in terms of controllability, observability, reveals that everything boils down to a relative cohomology computation. So if this guy vanishes, then that means the harmonic extension is unique. That means if you take a global section, a globally harmonic opinion distribution, then you can drive the entire system to that just by fixing those nodes at U and then forcing those opinions out stubbornly. If you want observability, if you have some collection of vertices that you want to, those are the ones you want to drive their opinions by using some user input U. Then the relevant cohomological obstruction here is going to be this guy. Now, I apologize for not defining relative zero-dimensional cohomology. The rough idea is you're looking at global sections, globally consistent solutions that vanish on that second term, in this case, U. Apologies for not giving careful definitions to all my terms, but there's just a little bit more that I want to say in the remaining minutes, because, okay, this is a fun model. This is a general model. I love this model. I love the fact that it uses some interesting mathematics, a little bit of the language of sheaves. But, I'm not 100% sure that this is actually how discourse works. It's a lot better than the cartoon model, but even in this model, the way that this diffusion is happening is I talk to my neighbors and I modify my opinions based on what I hear them say. That's not always the way it works. What sometimes happens is you listen to what other people say and you hold your opinions, but you modify how you express them. So here is what I think is the most interesting aspect of this model, where you have dynamics not on a sheaf, but among sheaves. Namely, I have dynamics on the space of discourse sheaves. Here's the idea. What I can do is evolve these, these linear transformations. These are just explicit linear transformations. You write the whole thing as a big old block matrix, and I can evolve them. I can evolve them according to a heat equation. What happens if we set things up in order to be able to do that kind of evolution? What we can do is evolve one of these maps, and hence all of them, by, roughly speaking, looking at what is happening to this edge. And then I take the data at that vertex V, and then I do the same thing with the other vertex where I take the data there, XU. Then I need to put some little negative coefficient out in front of this and hit this with XV transpose. Do this for every vertex edge pair. This is really a heat equation on the space of discourse sheaves. And the theorem here is that for any initial condition, this discourse sheaf will converge to the closest discourse sheaf, respecting the same underlying graph structure, that is, respecting the block structure, that has this opinion distribution as a global section, as a harmonic opinion distribution. Now, if there's no way to get consistency, that, this might, could get interesting. If you, of course, generalize to both the opinions and the sheaves evolving jointly, then you can get some interesting effects. In particular, what happens with a little bit of numerical simulation is that people, so to speak, learn to communicate better. Let's say that I've got a vertex V, vertex U, and I've got an edge E. Let's make it really simple, where all of these stalks are just one-dimensional. So everyone's talking about the same thing. Everyone's talking about what they think about my pink shirt. And the initial condition for U is positive, and the initial condition for V is strongly negative. And let's say that we start off with identity maps. So you just plainly express your opinion. Well, this is not harmonic. It doesn't match up. So evolve. So flow. The sheaf, the opinions, either or. What will happen in simulation is something like this. The opinions might modulate a little bit, but what really changes is the expression of opinions. And this guy right here has learned how to, not quite, for the sake of harmony. There's that. Okay, so we are out of time. There is, of course, much more that could be said. There's much more that should be done, including trying to get some data, playing around with this model, seeing how realistic we can make it. Absolutely. Including generalizing it to not just pairwise interactions, but multiple interactions, so that you have a higher dimensional simplicial complex as your base space. Yes, absolutely. Generalizing the coefficients, so that instead of working with vector spaces, we work with more interesting categories of data. Yes, and I have a few things to say about that as well, but not today. I'm going to thank you for your patience in listening to what is admittedly kind of a weird talk, but thank you, and I'd be happy to take questions.
Well, thank you for your weird talk, and weird and wonderful talk. And so let's all thank our speaker, either auditorily or virtually. And in the same vein, please feel free now to ask Professor Grice your questions, either by speaking up and unmuting yourself, or by writing them in the chat, and then I can read them out.
Hi, so I have a question, if that's all right.
Mm-hmm.
And it's perhaps not hugely, it's more about the sort of heat flow. You've got this heat flow on these sheaves. When I kind of think about the heat equation, I think about, I can really give it some sort of awful initial condition, and it still kind of manages to end up smooth. And then equally, if I do it in reverse, I can start with something nice and it can end up, coming from a really horrible initial condition. Is that even true when I think about this flow of these maps on this sheaves?
Yeah, I think it is. And in fact, in some cases, you can start off with an initial condition that is so inconsistent that the only way to have a harmonic opinion distribution at the end is that everybody is flat. Everyone is zero. Nobody cares about anything. That's, of course, not a good outcome, but depending on the structure of the sheaf, how it's programmed, think about a system where you got one-dimensional stalks everywhere around a ring, around a circle of agents with pairwise edges. If you have an odd number of lies, so that the whole bundle kind of looks like a Mobius strip, then there's no way you're going to be able to get a non-zero section of that bundle. So,
Cheers, thanks.
That's a form of kind of frustration you're hinting at there. I see.
right.
Okay.
There's no way to have an express consensus.
Another question for our speaker. Remember, you can also write it in the chat.
So the heat equation, you're still relying on the heat equation, which diffuses. How do you get polarization from that in this sort of network?
Now that's really interesting, because in this, polarization does not naturally come about. Maybe the most important next step to take is to start looking at things that are not just a straight up heat equation, that are not linear, but have some nonlinear terms. Now, in the literature, maybe one of the most popular models out there is the pronunciation Hegselmann Krauss, that is a sort of a selective listening model. So I'm only going to be influenced by people who are reasonably close to my opinion. And if you're too far away, I'm not going to listen to you. I'm not going to be influenced, even though we're sharing our opinions. That can definitely lead to polarization. We're able to model those with this setting by changing the dynamics to being just sort of piecewise heat equations. So it's not just a pure diffusion. But, there's so much more that I think one could do if you start looking at truly nonlinear dynamics. You start setting up reaction diffusion type equations. I bet you can get all kinds of crazy stuff. But this is very new work, and that's really untouched.
Thank you.
Hi, so you are using basically just a very simple graph structure, but in social networks you can easily assign weights to edges, which can represent the closeness of people and so on. So is there a way to incorporate this kind of information into the model?
Yes, there is. Thank you for that question. The way that we did this was to interpret those weights as something like a stubbornness, how much diffusion is happening across that edge. And a simple way to do this sort of illustrates the way that the way that I think you think about things, if you're thinking topologically, is what we do is we just build a sheaf over an augmented network. So to get weights incorporated, what we do is every vertex in the graph, you add a new parent vertex with an edge to the child. You make the parent stubborn, and you program the sheaf over that edge to have a coefficient in it for how much influence is happening. And what we can show is that has the effect of having tunable diffusion over each vertex, over each edge. That's one way to do it. I'm sure there are lots of other ways to get sort of tunable edge by edge parameters in the dynamics.
Thank you. A follow-up question. So is this also a way to kind of modify the metric structure on the graph from the harmonic distributions?
So the graphs that we're working with have no metric structure. They're purely combinatorial.
I mean the weights. So imagine you start with some weights, you run the discourse, and the discourse can severe some weights, severe some connections, new connections can form. Is there a way to capture that?
Oh, now I understand the question. My apologies. That's a really great idea. I have not included the weights in the dynamics, but I think that would be a great thing to look at.
Thank you.
Perhaps one more question as we as we close out here, if anyone would like to ask?
So yeah, perhaps I have, sorry, just another one. Just thinking of a sort of an application sort of sense, do you have a sort of an idea of the timescale in which this evolves? You know, if we were to give some sort of idea of, or, you know, if this is a population and it's doing something, kind of what the sort of time to get to this solution is?
Yeah, so the convergence rates are controlled by the spectrum of the Sheaf Laplacian. And that is such an interesting story. There's so much that we know about the spectral properties of the graph Laplacian and how it really influences and reflects the structure of the graph. The corresponding version of spectral graph theory, but for sheaves, is largely untouched fertile ground. Jacob Hansen wrote his PhD thesis on that, but there's just a huge amount of work to be done in terms of recapitulating spectral graph theory for sheaves over graphs.
Can I ask a quick question too, or do we have to be totally done?
Yeah, it's up to our speaker.
Sure.
I guess I know this is a bit skew to the topic, but I was just thinking, you know, what am I most interested in linear dynamical systems? And I guess the thing that comes to mind is probably like Koopman embeddings, and so the idea of, you know, building a linear dynamical system in a high dimensional space that when you project onto some lower dimensional space represents a nonlinear dynamics. And so, I mean, you know, probably there's, you know, if the equivalence of spectral graph theory hasn't been fleshed out, probably that stuff is completely untouched too. But I just wonder what you think about it.
I have no thoughts on Koopman stuff other than, well, let me put it this way. I have no opinions that I wish to express in public. Yeah.
Okay, thanks a lot.
Mm-hmm.
Okay, and with that, let's thank our speaker one last time for his excellent talk. And thanks to everybody for coming. And thank you, Professor Grice.
Thank you so much. I appreciate the invitation.
Absolutely. All right, everyone have a nice evening.